Okay, so slopes of polar curves. Well, the nice thing is that it is still derivatives, represents slopes and rates of change of polar curves, but we got to take into consideration that our polar curves are equations that have r's and thetas and not x's and y's. Now remember, the very first thing we do to the polar and rectangular was to kind of go back and forth between calling that coordinate xy and calling it r theta. And we talked about how to convert r's and thetas to x's and y's through our little shortcuts, which we'll talk about, remind ourselves here of in a second. So when I'm finding a slope or a rate of change, we got to be careful about what we're looking at. If I'm just looking at my r equation, and my r equation is like this one down below, 2 cosine of 3 theta, that is a function in terms of theta. So if I take the derivative of r, I'm really taking dr d theta. If I literally just take the derivative of these equations we've been throwing into our calculator. And obviously I could like notate that as f prime of theta. But what does that represent? That doesn't represent a slope of this curve. That represents a rate of change, or I'm going to even write it out, the rate at which the radius, I'll say, or r, is changing as theta changes, or theta increases, I guess. So what does that mean? So if I have, let's say, like a cardioid going around here, well, if I take this particular point on that curve and I calculate dr d theta at that particular point, take the derivative and substitute in whatever angle that is, that's going to tell me how fast this distance back to the center or the origin, how fast that is changing as I traverse through the polar curve. And that's not a slope. That's like a rate of change of the distance relative to the center as you're passing through. So that's, I mean, it is something, and we'll see in a minute that that's going to ask me, we're going to see something that's going to ask me that, but that's not slope. Slope is still dy dx. That's still dy dx. But the problem is if you remember, our x equation is r cos theta, and my y equation is r sine theta. Well, and on top of that, remember what r is. R is a function in terms of theta. So really, x is all in terms of theta, and y is all in terms of theta. So really, if I take the derivatives of these little components, I get dy d theta over dx d theta. So if I take the derivatives of each of these little individual terms, or expressions, I should say, equations, that would give me two relationships that I can divide. And obviously, hope you can see the algebra. Dy d theta divided by dx d theta. The thetas will cancel out, and d thetas will cancel out, and I'll get dy dx. Well, what does that mean I got to do? Well, that means I have to take the derivative in terms of theta of r sine of theta over the derivative in terms of theta of r cosine of theta. And that is how we find the slope of a polar curve. Now, if you look carefully, that means I'm taking the derivatives of these two equations. R itself is an equation. So that's an equation times sine that I'll have to take the derivative of. So anybody know what we're going to have to use here in a minute? Got an equation times sine, and I'm going to take its derivative. I'm going to have to use product rule. So product rule is going to be a common thing that we'll wind up seeing with these polar curves and their slopes. So let's see what's going on. Find the slope of this function at pi over 6, then use it to write the equation of the tangent line. All right, so let's at least get a quick graph of what this looks like. Again, we could plot points, but at some point, we do let our calculator take over and just see what's going on. I'm going to do a zoom 4. Okay, so it's a nice little 3-petal rose going through there. Give myself a little sketch of one so I can see it. Yeah, that's kind of okay. I'll just make a big dot there. I'll cheat. All right, and I want to know the slope at pi over 6. So I'm going to trace this and just trace it to pi divided by 6. And where is that? Okay, it's right there at the origin. Oh, I should have made my picture a little bit better. All right, so it's right there at the origin. So what and if I'm looking at my graph here, it looks like at that particular point, if I'm tracing, remember it's coming around like this. So it's going to have this negative sloping tangent line right there. So I know at least I'm going to have to get a negative slope. And so that particular point is my pi over 6. All right, so let's figure it out. So I want dy dx, and that means I'm going to take the derivative of the y equation. Now the y equation is r sine of theta. So r is 2 cos 3 theta times sine of theta. And then the derivative of x is now the x equation is r, I should have another set of parentheses in here, sorry, r cosine theta. Now, if I literally did the product rule up in the numerator and the product rule down in the denominator, I'm going to get a big expression in terms of theta, which then represents the slope at any angle on this polar curve. Well, I don't need to do that for all of them. Let's just do it specifically for theta equals pi over 6. So here I'm going to cheat a little bit. So now I'm going to go, and I'm going to go to my home screen, and I'm going to let my calculator do this for me. I'm going to go and do a math thing. It's been a while since we've done this. So I already have r in there already. So I'm going to bring up r1. And again, those people with the older calculators just use vars, y bars, polar y1. What am I doing? Wow, truck going by. And I want to do this at pi divided by 6. So what I'm doing is I'm letting my calculator evaluate this derivative at pi over 6. And just making sure I'm in radian mode. Yep, good. So I don't know about you, but that looks like -3 to me. So -3 is my numerator. And I'm just going to go in and do a second enter. And all I got to do take the derivative of x is I got to change this to a cosine. And so some weird number, -5.196. Oh, and now I'm realizing I said something that was wrong. All right, so I'm going to take -3 divided by my last answer, and I'm getting 0.577, which made me nervous about what I had just said before, but nobody called me on it. Hey, this is a positive number. Is that good? Well, yeah, because silly me, back here, I said that this was a negative sloping line. No, my y values were decreasing as going here. This obviously is a positive sloping line. What was I talking about? So that got a positive slope, and I now know that the slope of that line is 0.577. So that's pretty easy. So that's nice. Well, the next thing I got to do is now I want to, and so that was the question. I want to find the equation of the tangent line. So now what do I need? So I got a slope. What else do I need to write an equation of a tangent line? Well, I need a point. Well, how do I get my point? Well, I use x and y. So x is equal to r cosine theta, and y is equal to r, oops, I don't know why I'm putting parentheses here, r sine of theta. And I want both of these evaluated at theta equals pi over 6. But I think we already know what it's going to be. What's x, what's y? Anybody know? Well, I could obviously punch this into my calculator, but just look what, if I were to take pi over 6 and multiply it by 3, 3 times pi over 6 is pi over 2. What's the cosine of pi over 2? Cosine of 90 degrees? It's 0. That's where the graph hits the x-axis. So that whole thing goes to 0. In fact, this whole thing's going to go to 0. Didn't we know that this was 0, 0? Didn't we know right there it was hitting pi over 6 was right there at the origin? We saw it earlier in our graph. So I really didn't need to do that in this particular problem. So now putting them all together, y minus 0 equals 0.577, x minus 0. So I get the equation 0.577x. There is the equation of that tangent line. Now, remember, way back when, our calculator could do some stuff for us. Let's just take a quick peek here. Remember, my functions in is r in there. So if I, and my graph is already there, oops, my graph. So if I go to my second calc menu, usually there's a whole bunch of stuff there, but this time there's not. So first of all, value, if I wanted to know the value, I could just hit that and type in pi divided by 6, boom, 0, 0. So I wouldn't have had to do that work. And if I go back in, if I wanted to know the slope, I would have to do number 2, dy dx. Notice dr d theta is there, but that's not the slope. That's just a rate of change of the distance from the origin. I would have to do that, and then it's waiting for me to punch in where I want to be. So I'm just going to punch in a pi over 6, and boom, there it is, 0.577, that exact same value that we got over there. So your calculator can do a lot of this work, and I'll show you in a second why it's important for us to be able to do it with and without our calculator. But at least understanding the difference between dr d theta and dy dx is helpful when we're using our calculator. All right, let's look at a quick other one here. All right, so find the slope of this function and then write the equation of the tangent line. All right, so I want to get a good sketch. 3 minus 2 cos theta. 3 minus 2 cos theta. Zoom 4, what's this thing look like? Oh, it looks like a big cardioid. All right, this is nice and pretty. You can, yeah. In fact, that's not going to be good. I got to draw this a little bit more accurately. Come on, like this. All right. The reason being I knew that is because what's about to happen in a second. At pi over 2, well, you could probably take a guess of where this graph is at pi over 2, but I'm going to just hit trace and type in pi over 2 and see where I'm at. And sure enough, I'm right up there on the y-axis. That's what I was thinking where I would wind up being. Now, my picture is not really good. If you look on your graph, it definitely looks like that's going to be a negative sloping line. So I'm going to draw a tangent line that looks like it has a negative slope in my graph. Because it definitely does in my picture. All right, who wants to cheat? Okay, John wants to cheat, so let's cheat. All right, so what do I need to do to write an equation of a tangent line? I need a point and a slope. Let's go grab the slope. So I want dy dx at theta equals pi over 2. Again, if I was doing it by hand, I'd have to do the r sine of theta or r cosine of theta and the quotient of that. But in this case, I'm just going to go to second calc. Second calc dy dx, I hit dy dx. I'm just going to type in, just to be sure, pi over 2, that I'm at the right spot. And there it is. What's that look like to you guys? That looks like negative 2/3 to me. So it's negative 2/3. And then what else do I need? I need a coordinate. So now I'm just going to notate this. I don't even know if this is the notation of it. But I'm going to say, okay, what's the xy coordinate when theta equals pi over 2? Well, I can just go back into second calc, value, and just type in pi divided by 2. And it's at coordinate 0, 3. Which honestly, I think I can even see that in my diagram, 0, 3. And so there we go. Y minus 3 equals negative 2/3 x minus 0. Equation of a tangent line to a polar curve. So again, did it by hand and then did it with our calculator, still giving me the same thing. Notice I have not at all talked about dr d theta. Again, that would just be the distance that each point is changing its distance relative to the origin. All right, so kind of easy. And so the last thing I just want to show you is what it looks like on the AP exam. So what some of you will be missing out on next year, not joining us in BC, but some of you that will be joining me. This was from 2 years ago, so it was super recent. And this is the graph that they gave them. They gave them these two polar curves, and this was a no calculator problem, which was, I remember it was a shocker when it came out, because people were like, oh, but I thought we could use a calculator for all of these. Well, no, that's why we learned how to do them without, too. So I'm going to keep this graph handy. I didn't want to print it all on the same page, so I've got that graph kind of at my side here, ready to go. All right, so let's see what we got. We got the graphs of the polar curves, r equals 4. Well, that, I don't know. When a polar curve's r equals 4, what's the shape of that graph?
A circle.
That's the circle, right. So that's this one. That's r equals 4. I'm going to label it. And then obviously the other one must be this cardioid, 3 plus 2 cos theta. Well, it's almost exactly like the one I did before, 3 minus 2 cosine theta. So 3 plus 2 cos theta. That's my cardioid there. And the curves intersect at pi over 3. Oh, that's nice. They gave me those. So theta equals pi over 3 right there. Remember, zero's over here, comes around pi over 3. And the next time they intersect is down here at 5 pi over 3. Okay, that's pretty easy. All right, so there's all my stuff. Let's see what they're going to ask me to do. So let R be the shaded region inside the graph of R and also outside of the graph of the other R, as shown in the figure. Write an expression involving an integral for the area of region R. All right. So area of, I'm not going to even call it region R, but the area of region R. Well, do we remember what the formula was yesterday? What that integral was? Integral of 1/2
R squared. 1/2 the integral of R squared.
Right. 1/2 integral of R squared d theta from theta 1 to theta 2. So in this case, it's 1/2. Okay, now let's think of game plan. How am I going to find that area of region R? What am I going to do? Now remember, all of my areas are stemming out from the center. So anybody got an idea of what I could do to calculate the area of just between these two curves? Well, first of all, are these curves bounded within the same interval? And the answer is yeah. Here's this circle out here from pi over 3 to 5 pi over 3. And then here's this cardioid from pi over 3 to 5 pi over 3. Well, if I were to first find the area of the circle all the way around, and then subtract out the area bounded by the cardioid, that would give me the difference between the two, and that would give me my area between them. So it literally is going to be the area between them, or the difference of these two functions squared. So the circle squared would be that area, d theta. But since I'm on the same interval, I'm just going to then subtract out the inner cardioid squared, d theta. And right there, that alone would have gotten us 3 points on the exam. My next page is the actual scoring guide. So there it is, 1/2 4 squared minus the other 1 squared. That got you 3 out of 9 points just for writing that integral. That's it. So that's pretty easy. Part B, find the slope of the line tangent to the curve. Ooh, they don't even want the whole equation, they just want the slope. All right, sweet. I'll just grab my, oh, wait a second. I don't get to use my calculator. So calculators put aside, how do I find the slope of a polar curve? All right, so let's scoot up here. dy dx. All right, so remember this is dy d theta over dx d theta. And that means I'm taking the derivative of, okay, what was the y equation? No, x's and y's. Let's see if I can remember. X is r, what is x? Is x cosine or sine? Any remember? I don't have it memorized, guys. I just have it in my, I have this in my head. And that means if I want to find this x side, it is adjacent to the theta, and which trig function gives me adjacent over hypotenuse? That's cosine. And the other ones are sine of theta. Now, some teachers teach it that, oh, x, y goes in alphabetical order, so CS goes in alphabetical order. Well, yeah, that's true, but it's just by happenstance. So I just remember in terms of my relationships to my triangles. All right, so here we go. I need r cos, for y, r sine of theta. So what was r? R was 3 plus 2 cos theta, this is y, so it's sine theta. So I'm going to take the derivative of that. Okay, so now the derivative of x, the x equation, is r cosine theta. And I want to be doing this at pi over 2. All right, so this is something we didn't have to do before because we kind of cheated. So now I actually have to take the derivative there. So I have to do product rule. But it's not going to be that bad. You'll see in a second. So 1 d2 plus 2 d1. And yeah, do people have to do this on the exam? Yeah. I remember people came out, they're like, oh my gosh, I didn't know what I had to do. Yeah, but we did it. So 1 d2 plus 2 d1. So that's not awful. And not only that, but good grief. Could they have given me an easier angle? Well, probably. They could have given me 0. But pi over 2, that's a nice easy angle. Pi over 2 has usually either 0s and 1s. All right, cosine of pi over 2. Cosine of pi over 2, that's 0. Ooh, boy. Anywhere that there's a cosine, it's going to 0. Lots of zeros. What's the sine of pi over 2? Well, that's 1. So all those sines are going to go to 1s. So now it's just kind of carefully dissecting what I got left here. What does it look like? I got a -2 up top. Uh-oh, something's not right here. Did I mess up? 1 d2 plus 2 d1. Uh-oh. I did this earlier. Did I mess up? Oh, I'm okay. Anybody see where it is? I'm seeing 0 and 0. I can't have a denominator of 0.
3 plus.
Yeah, 3 plus right here. Thanks, Devin. So I have a denominator of 3. That goes to 0, but this was a little addition here. I think I'm done. How many points did that grab us on the exam? 3 more points. And notice, you can see they're doing, well, here they're doing the method that we did down here. There's 2 different methods. You can memorize a formula, which I don't have you guys do. Or we can actually work with what we're doing here. Here's our product rule and all that kind of stuff. They actually distributed it out first and took a derivative of that. So I think it's much easier this way. All right, last part, and then we're done. All right, so now we have a particle moves along the portion of the curve from 0 to pi over 2. So now we're just on that particular cardioid. The particle moves in such a way that the distance between the particle and the origin increases a constant rate of 3 units per second. Hold on a second. Let me read that again. The particle moves in such a way such that the distance between the particle and the origin increases at a constant rate of 3 units per second. I don't know about you, but that sounds like something I've talked about today already. The distance between the particle and the origin changes 3 units per second. That sounds like dRdt. dRdt is 3. Does that make sense? The rate at which the distance between there and the origin is changing 3 units per second. Now careful, this is dRdt. We've talked about drd theta. Let's keep reading on. Find the rate at which the angle changes with respect to time. So I'd like to find rate at which the angle changes. D theta with respect to time. dt when theta equals pi over 3. Hey, 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 guess what this is? What kind of a problem is this? This is a related rate problem. So in a related rate problem, we're going to use some little symbolic notation here to kind of help me out here. So I know that, all right, let's maybe do it. There's a couple ways you can approach this. If I'm trying to find d theta dt, yeah, that's fine. All right. Well, what do I know? I know dr dt. Well, clearly they're not equal because things aren't canceling out. What would I have to multiply dr dt by in order for things to cancel out and give me d theta dt?
D theta dr.
D theta dr. Does that make sense? Because then my, yes, my dr's cancel out. Okay, do I know dr dt? Yup, they said it was 3. Do I know d theta dr? D theta dr. I don't know d theta dr, but with my equation, r equals 3 plus 2 cos theta, I know I can get dr d theta, the derivative.
And you could flip it.
And I can flip it, exactly, and that's exactly what we're going to do. So -2 sine of theta is the derivative. I am evaluating this at what angle? Pi over 3. So -2 sine pi over 3, quick little triangle, that's 60 degrees. So that's √3, 1, 2, and the sine is √3 over 2. So -2 times √3 over 2 equals negative, I know I'm running out of room, negative √3. But we got to flip it. And so therefore, d theta, the rate at which the angle is changing with respect to time, is 3 over -√3. And you could leave the answer like that, but if actually you did rationalize the denominator, you wind up getting -√3 altogether. But that's not necessary. So it's a little weird related rate problem, but we could fish our way through it, working with the notation. And there is an example of pulling in and using dr d theta, and not necessarily using that for slopes. So obviously that's going to get us the last 3 points here in this particular problem. And they're
Wow.
the same way I did too. So,
Oh, we did get it.
oh, did we?
Yeah.
Oh, rats. I would have gotten an 8 out of 9. Shoot. So this is d theta dt. Theta is being measured in radians. T is measured in seconds. So radians per second. Ugh, that would have been awful if I'd missed that point. Good call. Good call. So a little bit of working with our calculator and a little bit of working with by hand. Obviously, those of you joining me next year, you would have to be able to do both. So not too bad. And that kind of wraps up us working with polar curves.